Swayam Prabha. Digital India. Educated India.
Now at this point we have to find out where our objective function value is going to be maximum. For that reason we know the objective function slope or objective function value. So that line we can represent as this slope, and we need to move it. We'll start from one end and we'll start moving it as it increases. So we started with z equal to 60, z equal to 100, and if we keep on moving we'll find that it is going to touch one extreme corner beyond which it cannot go because there is no feasible solution, and that point in this case is actually this point. This is our solution. So if you recall the solution in the previous slide, which I'll go, the number of doors are 20 and number of windows are 60. So number of doors, this is 20, and number of windows, if we go this direction we'll find that windows are equal to 60. So that is my optimum solution, and this has to be reported as a solution. So in the graphical method it is quite easy, and however you have to draw the graph, and it is quite possible if the number of variables are up to 2, which you can represent it in a two-dimensional surface. Since we are using the axis as which represent the design variable or the decision variable, and if our problem has more than 3 or 4 design variable, more than 3 you can say, then it is not possible for us to plot it on a paper or understand it, view it in this way. So in those cases there are techniques, mathematical techniques to solve. I'll be discussing that as part of the linear programming problem. I hope you understood the graphical solution method. We'll look into the few cases, what are the different cases which are possible and which we had discussed earlier. In this case you got one particular solution. We also said in certain cases there could be multiple solutions, or there could be no solution at all. So we'll be discussing those things. So let us look into this special case of the problem where we have tweaked the constraint by changing this particular constraint. So our objective function still remains same, and we have changed both the constraints. Now if you look into the second constraint, that is represented by this orange line. So if I say this is the first constraint, this is the second constraint. So first constraint is represented by this one, and the second constraint is represented by the orange line. Now if you carefully look into the first constraint and the objective function, it represents the same slope, which means once we identify the feasible region, in this case the blue line feasible region is going to be any point on the inner side of the lines or the sections I am hatching, and for the orange is going to be this. We also said in this particular problem that the variables are going to be greater or equal to 0, so we cannot go anything on the negative side. So our feasible region is going to be this. Now in this feasible region, we found that the slope of the blue line and the objective functions are same. So once we are trying to fit the objective function and slide it from one end to the another, we'll see that it will go and touch the blue line along it, or the first constraint along it. So any point or any further if we go, we'll enter into the infeasible region. So in this case, we'll find that all the solutions along this blue line are feasible and optimum for this particular problem. So we do not have just one single value, rather we have multiple values in this. So eventually this particular problem becomes an example for multiple optimum solution. Now we'll be looking into the problem, similar problem. The objective function remains same, the constraint, first constraint remains same, second constraint we have removed and we introduced a new constraint, as this should be greater than 30, and this is the third constraint and this should be greater than 20. So the first constraint, the blue line, it says this is my infeasible region, so the other side is the feasible region. The second constraint, represented by this yellow line, says that it should be greater than 30, so this is my infeasible region, and this side is my feasible region. For the third constraint, since it is greater than 20, so this is my infeasible region, and this side is my feasible region. So if we look closely now for the solution, this region is feasible, this region A is feasible for the constraint, this is 1, this is 2, and this is 3. So A is feasible for 1 and 3, but not feasible for 2. B is feasible for 1 but not feasible for 2 and 3. C is feasible for 1 and 2 but not feasible for 3. D is not feasible for any of the constraints. E is feasible for 2 and 3 but not 1. F is feasible for 3 but not 1 and 2. So there is also one more region which is of this triangle, which we can call it as G. This region is infeasible for all the 3. So overall we see that we do not have a region which is feasible for all the 3 constraints. That means any solution we obtain, one or the other constraint is going to be violated. So in other words, we do not have any infeasible solution. So a problem may also come or may also have infeasible solution. It depends on the problem. And it was true even in case of the multivariable optimization problem or nonlinear programming problem, and This we are seeing it here as well for the linear programming problem. We'll look into the another case, which is for the third case. In this case, we want to maximize this particular function. This is our first constraint, this is our second constraint, this is our third constraint, and this is our fourth constraint. So the first constraint, which is represented by the blue line, which is represented here, is greater than equal to 2. So it clearly says that the values should be greater than 2. So this is my infeasible region. So on the other side I have the feasible zone. If I look into the second constraint indicates that this is my infeasible zone. So anything on the other side is going to be feasible. So in light of the first constraint, the second constraint is ineffective. The first constraint will take care of the second constraint related area. Now we should look into the third constraint. So the third constraint is represented by the green line, which says that this bottom part of the green line is infeasible and anything above is going to be feasible. The fourth constraint says that the variable x2 is greater than 0. So by the way, this is my x1 and this is my x2. So x2 is greater than 0, so we are saying this side is infeasible. So looking into all the area, we can say that this blue line and the green line on this side represents the feasible area or feasible search space. Now if this is my feasible search space, which is good, if we try to find out the maximum objective function value, which is represented by this gray line, and if we try to slide this gray line, we see that we can keep on increasing this value as we move. So there is no end to it. Which means we cannot obtain the optimum solution even though we have a well-defined feasible region. In other words, the problem or the constraint actually created a feasible region which is unbound for this particular objective function, and hence we cannot obtain the solution. So this is the third situation. Even though we have the objective function and the constraints and we do have the feasible region, but still we may not have the optimum solution because the feasible region is unbound and for this particular objective function problem. So in a optimization problem, we can always get into one of this situation. If we understand this, now we'll be quickly moving into the factors which we need to know of the linear programming problem, that is the standard maximum form of the linear programming problem. Linear programming problem in its standard form should have the objective function which required to be maximized. All the variables are expected to be non-negative. The constraints are expected to be less than a constant value, and the constants of the constraints are expected to be non-negative value. So this is the standard format of the linear programming problem. Some authors or some places you may find the reverse of it. The solution and the method is slightly going to change accordingly. In this class, we are going to consider this as the standard problem, and the solution and the methods will be for this particular format. In case if it is not in the standard format, first thing we have to bring the problem into the standard format before applying any method. So if this standard format or standard maximum form, if we want to see it in a mathematical format, it can be represented as maximization of the objective function. We can also have a constant subject to, where we say these are the equality constraints and these are the inequality constraints, and we said the variables are supposed to be greater equal to 0, so this is greater equal to 0. Now the second part here is that we said at the beginning of the linear function, at the beginning we discussed about the linear function. At that point we said it must have a definite solution for the function. Now we have the inequality constraint, so inequality constraint is not going to give us a definite solution, but rather more than one solution or a lot of solution. So for this part we need to introduce a slack variable and convert the inequality constraint into an equality constraint. We'll learn about that in the next class. So if you look into this particular problem, we also see that this component is going to lead to some variables. In this case, if we assume that there are n design variables or the decision variables, and this part, the constraints are going to lead to certain number of equations. If we say that this number of equations are j, we know that if you have n unknowns, and same number of equations, then we can solve it and find the value of each unknown. So if n becomes, or j is equal to n, then we can actually solve this particular problem using a system of equation solution process. In all other cases, we have to use certain technique to find the solution. So we'll know more about those methods and the techniques and how to introduce the slack variable in the next class. However, I believe in today's class we are very clear about the linear function and the standard format of the linear programming problems. So I hope you understood the linear functions and as well as the linear programming problem, the standard format of it. Now you can actually look back into the nonlinear programming problems which we had discussed all the classes in the previous classes, and you'll see that the difference between the nonlinear and the linear is the function. So all the functions which we have in the linear programming are going to be the linear function, which was not true in case of the nonlinear. In the nonlinear we had objective functions which are nonlinear, or the constraint is nonlinear. So one of the constraint or the objective function, the moment it becomes nonlinear, we have to use the nonlinear programming problem solution techniques. Whereas if all of the constraints and the objective function found to be linear, then we can use the linear programming problem. So today was the start of the linear programming problem. We saw the graphical solution method. We'll look into more details about other methods, because we understood the graphical solution method is limited to 2 variable or the 3 variable optimization problem. So the linear programming problem is eventually or actually a multivariable optimization problem. However, the functions are linear. Now, if the number of variables are more than 2 or 3, as I said, it is difficult to represent graphically. So we need to rely on some other technique to solve that, and those techniques for different types of problem we'll be discussing in our next class onwards. So till then, thank you and see you in the next class.